Two amateur astronomers, working independently, captured images that challenge a century of cometary science. 4 days apart, different hemispheres, same impossible geometry. While NASA released featureless spheres, Diego and Craggs resolved 4-point plasma stars and rigid blue halos that looked manufactured. The object is 3I-ATLAS, and it's not behaving. Its tail vanished. Its symmetry holds at 94%. Its brightness spikes when physics says it shouldn't. Tonight we're dissecting every anomaly through rotation paradoxes, plasma physics, magnetic confinement, and the uncomfortable fact that if you were designing an interstellar craft, you'd probably build something that looks exactly like this. AI agrees, engineers agree, nature apparently disagrees. Stay until the end, because whether Atlas is natural or not, the question itself represents a threshold we've never crossed before. If you're as captivated by this mystery as I am, go ahead and like and subscribe so you catch every development as this story continues to evolve. Leave a comment letting me know where you're watching from, what time it is in your corner of the world, and whether you think we're seeing the complete picture on these potentially paradigm-shifting discoveries. Part 1. The Night Everything Changed. On November 20th, 2025, an amateur astronomer named Diego pointed his 11-inch backyard telescope at a fuzzy patch of light moving through the constellation Camelopardalis. He wasn't expecting to make history. He was just another hobbyist chasing comets, stacking exposures in his driveway while his neighbours slept. But when he processed his images 3 hours later, what appeared on his monitor made him question everything he thought he knew about celestial mechanics. The object designated 3I-ATLAS, our third confirmed interstellar visitor, wasn't behaving like a comet at all. Instead of the expected blob of diffuse gas and dust, Diego's images revealed something that looked engineered. A perfect 4-point plasma star, cross-shaped, emanating from a central core with geometric precision that made his hands shake as he adjusted the contrast. This wasn't sublimation. This wasn't random outgassing. This was structure. 4 days later, on November 24th, another amateur named Craggs captured the same object from a different hemisphere. His 8-inch reflector and consumer-grade CMOS camera, equipment you could buy for the price of a used car, resolved details that billion-dollar space agencies somehow missed. Craggs saw a rigid white core surrounded by what he described in his forum post as a blue halo, uniform and symmetric, glowing with an intensity that seemed to defy the chaos typically associated with Comet Comets. The glow appeared contained, almost deliberate, hugging the nucleus like a force field in a science fiction film. Both men used mid-tier equipment, the kind serious amateurs save up for but nothing approaching professional observatory specifications. They took thousands of short exposures and stacked them using free software, a technique that enhances signal and reduces noise. The results were sharper than anything NASA had publicly released. And that's where things got uncomfortable. Within hours of posting their images to astrophotography forums, the reaction split into 3 camps. Some dismissed the geometry as processing artifacts, the result of over-sharpening or stacking errors that create false patterns. Others, more experienced imagers who understood the mathematics of image processing, recognized immediately that these patterns were too consistent, too repeating across multiple frames to be algorithmic ghosts. A third group, smaller but vocal, whispered the question nobody wanted to ask out loud. What if this thing isn't natural? The forums erupted. Accusations flew. Some claimed Diego and Craggs had fabricated the images for attention. Others demanded they release their raw data, which both men did within 24 hours, only deepening the mystery when independent analysts confirmed the geometry was present in the unprocessed frames. The structure was real. It was there, and it made no sense. Meanwhile, NASA's publicly available imagery of 3I-ATLAS showed a featureless sphere, slightly elongated, glowing uniformly without any of the structure amateur astronomers were capturing. The discrepancy was jarring. Official images looked like someone had smeared Vaseline on the lens, while backyard telescopes were resolving geometry that suggested order, symmetry, intention. How does a hobbyist with a few $1,000s of gear outperform spacecraft equipped with instruments that cost more than small nations' GDP? The question gnawed at anyone paying attention. Some pointed to the technical realities of spacecraft imaging. Moving targets blur during long exposures. Sensor binning, where pixels are combined to reduce noise, smooths out fine detail. Bandwidth limitations mean only compressed, downsampled images get transmitted to Earth in real time. All legitimate explanations, all technically sound. But none of them explained why multiple independent amateurs, using different equipment from different locations, were all capturing the same structured geometry. Image stacking, the technique both Diego and Craggs used, works by taking advantage of statistics. Noise is random, signal is consistent. When you align and average hundreds or thousands of frames, the noise cancels out while the actual photons from the object reinforce each other. The result is an image with far higher effective resolution than any single exposure. It's why amateurs can sometimes see details professionals miss, not because their equipment is better, but because their methodology is different. They have time, they have patience. They can sit in their driveways for 6 hours capturing frame after frame, while a space telescope has to move on to the next target on a packed schedule. But the geometry Diego and Craggs captured wasn't just sharper, it was fundamentally different in character, revealing organisation where there should be chaos. Interstellar objects have a history of surprising us. When one Oumuamua tumbled through our solar system in 2017, it accelerated away from the Sun without any visible outgassing, violating our understanding of how inert objects move in space. Comet 2I Borisov, our second interstellar visitor, appeared almost too pristine, its chemical composition matching theoretical models of primordial comets with eerie precision. Now 3I-ATLAS arrives, and instead of answering questions, it multiplies them. The 4-point star Diego captured wasn't uniform in intensity. The arms of the cross showed brightness gradations, subtle but measurable, suggesting either rotation, directional emission, or something far stranger. Craggs's blue halo appeared in wavelength consistent with ionized carbon monoxide common in comet comae, but the distribution was wrong. Natural comae are messy, shaped by solar wind, radiation pressure, and the chaotic tumble of an irregular nucleus. This was smooth, contained, almost manufactured in its precision. The tension at the heart of this mystery is simple but profound. If 3I-ATLAS is just a comet, it's behaving unlike any comet we've ever studied. And if it's not a comet, then what we're looking at is an object that travelled light years through the emptiness between stars, survived impacts with interstellar dust, at velocities that would vaporize anything fragile, and somehow maintained a geometry so precise that cheap telescopes can resolve it, while space agencies show us blur. The glow, the symmetry, the rigid structure, these are just the opening notes of a symphony that gets stranger with every observation. Because what came next, what Diego and Craggs would capture in subsequent nights, would make the 4-point star and blue halo look tame by comparison. The tail was about to vanish, the geometry was about to tighten, and the brightness was about to spike in ways that violated every model of cometary behaviour we've spent centuries building. This isn't just an anomaly, this is a fracture in our understanding of what's possible. Part 2. The symmetry problem. Symmetry in nature is rare, and when it appears, it tells us something fundamental about the forces at work. Snowflakes form hexagonal patterns because of the molecular structure of ice. Flowers arrange petals in Fibonacci spirals because of growth optimization. But these symmetries emerge from simple rules applied millions of times, not from the chaotic, violent process of a comet hurtling through space while vaporizing its own surface. When Diego and Craggs processed their images of 3I-ATLAS through symmetry analysis software, the results were so improbable, they initially assumed the algorithm had malfunctioned. The software compared the left and right halves of the coma, pixel by pixel, measuring how closely they mirrored each other. For a typical comet, you'd expect symmetry scores in the range of 30 to 50%, reflecting the inherent irregularity of sublimation jets, tumbling rotation, and asymmetric heating. 3I-ATLAS scored 94%. That number doesn't just suggest organisation, it screams it. To understand why this is so wrong, you need to picture what a comet nucleus actually is. It's not a smooth sphere, it's a tumbling, fractured chunk of primordial ice and rock. What planetary scientists affectionately call a dirty snowball, or more accurately a snowy dirt ball. The surface is pockmarked with craters, ridges, and fissures. As sunlight heats one side, ice sublimates, vaporizing directly from solid to gas and creating jets that erupt from specific locations. These jets are directional, uneven, and change as the nucleus rotates, exposing different facets to the Sun. The result is a coma, a cloud of gas and dust that looks like someone threw a handful of glitter into a wind tunnel. Asymmetric, chaotic. Definitely not 94% bilaterally symmetric. Yet here we are, staring at images that suggest 3I-ATLAS is producing a coma with geometric precision that would make an engineer proud. Some argue the symmetry could result from rotational averaging. If the nucleus spins fast enough, individual jets blur together, creating an apparently uniform glow. It's like a ceiling fan, which appears solid when spinning at high speed even though it's just blades with empty space between them. The math is plausible. Rotate fast enough and asymmetries average out. But here's the problem. Comets that spin rapidly show other telltale signs. They develop equatorial bulges. They fragment more easily because centrifugal forces overcome the weak gravity holding them together. They produce characteristic light curves, brightness variations that match the rotation period. 3I-ATLAS shows none of these signatures. Its brightness is stable, not pulsing. Its shape appears rigid, not deforming. And most troubling, the rotation rate required to produce this level of symmetry would be so high that any loosely bound object would fly apart within hours, scattering debris across millions of kilometers. It's a paradox. To create the symmetry, ATLAS must spin impossibly fast. But to survive that spin without disintegrating, it must be impossibly strong. Throughout history, amateur astronomers have occasionally reported geometric patterns in comet comae, and most have been debunked. Image compression artifacts can create false structure. Overprocessing can introduce patterns that aren't there. Optical aberrations in poorly collimated telescopes can distort point sources into crosses or stars. But those explanations fall apart when multiple observers, using different equipment, different locations, different atmospheric conditions, all capture the same geometry. Diego used a Schmidt-Cassegrain telescope with a specific optical design prone to diffraction spikes. Craggs used a Newtonian reflector with a completely different optical signature. Their cameras had different sensors, different pixel sizes, different quantum efficiencies, yet the symmetry appeared in both datasets, consistent in position, consistent in morphology, consistent in wavelength distribution. This is the hallmark of a real feature, not an artifact. Something about 3I-ATLAS is generating organized light. Natural processes can sometimes mimic organization. Planetary nebulae, the glowing shells of gas expelled by dying stars, often show striking symmetry, likely shaped by magnetic fields or binary companion stars. The hexagonal storm at Saturn's North Pole maintains its shape for decades, a consequence of atmospheric dynamics and rotation. But these are steady-state systems, sustained by continuous energy input. A comet is a dynamic, decaying system, bleeding mass into space with every second it spends near the Sun. It's falling apart in real time. For it to maintain symmetry, it would need to constantly regulate its outgassing, compensating for changes in solar heating, rotation, and surface erosion. That requires feedback mechanisms, sensors, control systems, language borrowed from engineering, because nature doesn't typically operate with that level of active regulation. The possibility of a transient outburst event, a sudden symmetric eruption of gas, has been floated as an explanation. Comets occasionally experience outbursts where subsurface ice pockets vaporize explosively, temporarily brightening the coma. If such an event were perfectly centered on the nucleus, it might produce momentary symmetry. But outbursts are chaotic by definition, driven by subsurface fractures and stress release that can't be symmetric. And more damningly, the symmetry in 3I-ATLAS isn't momentary. It persisted across multiple nights of observation, from November 20th through at least November 28th, captured by over a dozen independent observers. This isn't a flash. It's a sustained configuration, maintained despite the comet's motion, despite changing solar angles, despite the violence of sublimation. Sustained symmetry demands sustained organization. Here's where the conversation gets uncomfortable. If we strip away assumptions and just describe what we observe, we'd say 3I-ATLAS appears to be actively maintaining its coma geometry. Maintaining implies regulation. Regulation implies response. Response implies, at minimum, a system that monitors its own state and adjusts accordingly. We don't have a natural precedent for that in comets. We have precedent in spacecraft, in satellites with attitude control systems, in probes that use thrusters to maintain orientation, but suggesting that parallel invites ridicule, accusations of pseudoscience, and immediate dismissal by mainstream astronomy. So the symmetry hangs there, 94% bilateral organisation, unexplained and unexplainable by conventional models. And the question no one wants to answer out loud is this: is 3I-ATLAS actively maintaining its shape? And if so, what does that tell us about what it really is? The implications are staggering, the evidence is mounting, and the next piece of the puzzle is even stranger. Because the symmetry wasn't the only thing defying physics. The tail was about to do something tails aren't supposed to do. Part 3. The vanishing tail and the inverted coma. Comet tails are supposed to be simple. Solar wind, a stream of charged particles blowing out from the sun at 1,000,000 miles per hour, pushes gas and dust away from the comet's nucleus, creating a tail that always points away from the sun like a windsock in a cosmic breeze. The tail stretches for millions of kilometres, a glowing streamer visible even to the naked eye for the brightest comets. It's one of the most reliable phenomena in astronomy. Predictable, consistent, governed by straightforward physics. So when 3I-ATLAS's tail started misbehaving, it wasn't just surprising, it was profoundly wrong. On November 20th, Diego's images showed something that shouldn't exist. A toroidal tail flattened into a ring, wrapping around the nucleus instead of trailing behind it. 4 days later, Craggs captured something even more disturbing. The tail had almost completely vanished, collapsed into a tight halo that clung to the coma like the object had swallowed its own exhaust. To understand how bizarre this is, imagine throwing a handful of sand into a river. The current carries it downstream, spreading it into a long plume. The sand doesn't circle back and wrap around your hand. It doesn't suddenly reverse direction and cluster near the source. That would require forces opposing the flow, pushing back against the current with equal or greater strength. In space, the solar wind is that current. For a comet's tail to flatten into a ring, something has to be redirecting the outflowing gas and dust, bending it perpendicular to the radial direction, confining it into a toroidal structure. Magnetic fields can do this. Rapidly rotating plasma can do this. But both require energy and organisation far beyond what we expect from a passive chunk of ice. Ring-shaped distributions in cometary comae have been observed before, but they're fleeting and poorly understood. In 1997, Comet Hale-Bopp showed transient spiral structures in its inner coma, likely caused by rotating gas jets. Those spirals lasted hours, maybe days, before solar wind shredded them. 3I-ATLAS toroidal structure persisted for at least 4 days and possibly longer, stable enough that multiple observers captured it independently. Stability in a dynamic environment like a coma requires continuous maintenance, continuous input of energy or momentum to counteract the forces trying to tear the structure apart. Solar wind pressure alone should have ripped the ring apart within hours, yet there it was, frame after frame, night after night, defying the very forces that should have destroyed it. The November 24th images from Craggs introduced a new level of strangeness. The ring had tightened, compressing inward until it was barely distinguishable from the coma itself. The tail, that long streamer that defines what a comet is, had effectively disappeared. What remained was a compact glowing sphere with a faint blue halo, looking less like a comet and more like a miniature magnetosphere, the kind of protective bubble that surrounds planets with active magnetic fields. Earth has one. Jupiter has one. Comets do not. They're too small, too cold, too geologically dead to generate the dynamo action required for planetary-scale magnetic fields. Yet the visual resemblance was uncanny, as if 3I-ATLAS had somehow wrapped itself in a protective cocoon, suppressing the very processes that should make it visible. The brightness data compounded the mystery. Comets brighten as they approach the sun because increased solar heating vaporizes more ice, expanding the coma and tail. It's a smooth, predictable curve. 3I-ATLAS didn't follow that curve. Its brightness spiked on November 22nd, a sudden increase not correlated with any change in solar distance. Then it dimmed slightly before spiking again on November 26th. These fluctuations occurred over timescales of days, far too rapid to be explained by changing heliocentric distance, and they occurred while the tail was collapsing, which should have made the comet dimmer, not brighter. It's as if the object was concentrating its energy, pulling the diffuse glow inward, intensifying the core while suppressing the tail. That's not how passive objects behave. That's how active systems behave when they're reallocating resources. Multiple observers across different continents reported the same toroidal morphology, eliminating the possibility of isolated equipment malfunction or regional atmospheric distortion. One observer in Australia, another in Spain, a third in Chile, all captured the ring structure within a 12-hour window on November 20th. When astronomy forums compared their images side by side, the consistency was eerie. Same tilt angle, same relative brightness distribution, same blue coloration in the halo. This wasn't artifact, this wasn't noise, this was a real, physical structure surrounding 3I-ATLAS, behaving in ways that no natural comet coma should. The inverted coma hypothesis emerged from these observations. Instead of gas and dust trailing behind the nucleus, pushed by solar wind, the material appeared to be circulating around the nucleus, trapped in a stable configuration. For this to happen, you need a confining force. In laboratory plasma physics, magnetic fields confine charged particles into toroidal shapes, the basis of fusion reactor design. In space, planetary magnetospheres trap solar wind particles, creating radiation belts. But those systems have active magnetic fields, generated by internal dynamos or induced by external fields. Comets are inert. They don't have dynamos. They don't generate fields. Unless, of course, this one does. The speculation grew darker with each new image. If 3I-ATLAS is suppressing its tail, why? Comets have been shedding tails for billions of years without issue. It's fundamental to their nature. Suppressing a tail would be like suppressing evaporation from boiling water. You'd need to actively counteract the natural process. The only reason to do that, the only conceivable motivation, is stealth. A large, diffuse tail is visible from great distances, a beacon announcing the comet's presence. A compact, dim object is harder to detect, harder to track, easier to overlook. That thought, that uncomfortable notion that 3I-ATLAS might be trying to reduce its visibility, infected the forums, whispered in private messages, dismissed publicly, but gnawing privately at anyone who stared at those images long enough. The vanishing tail and inverted coma opened doors to ideas that sound like science fiction but rest on observable data. The next sections would explore those ideas, diving into plasma physics, magnetic confinement, and the uncomfortable parallels between what we observe and what we'd expect from engineered systems. But before we go there, sit with this image, an object travelling through interstellar space for millennia, glowing with a symmetric blue halo, its tail collapsing inward, its brightness pulsing independently of solar heating. Either we're witnessing the most anomalous natural comet ever recorded, or we're witnessing something that was never a comet to begin with, and the data, cold and unyielding, keeps pointing toward the latter. Part 4. NASA versus the backyard telescopes. The disconnect between official imagery and amateur captures of 3I-ATLAS wasn't just noticeable. It was glaring, almost offensive in its magnitude. NASA's publicly released images, captured by spacecraft and ground-based observatories with budgets measured in billions, showed a fuzzy, elongated blob. No structure, no geometry, no blue halo. Just a smear of light against the black. The kind of image that tells you something's there without revealing what it actually is. Meanwhile, hobbyists with gear purchased on credit cards were resolving 4-point plasma stars, symmetric toroidal rings, and rigid cores with surrounding halos. The cognitive dissonance was too large to ignore. Either the amateurs were seeing things that weren't there, or the professionals were missing things that were, and increasingly the evidence favoured the latter. Spacecraft imaging presents unique challenges that ground-based telescopes don't face. When you're photographing a comet from a spacecraft travelling at tens of thousands of kilometres per hour, the target is moving relative to your position. Long exposures, necessary to gather enough light from faint objects, result in motion blur. The comet becomes a streak instead of a point. To compensate, spacecraft use shorter exposures and average multiple frames, a technique called frame stacking, ironically the same technique amateurs use. But spacecraft have bandwidth constraints. Transmitting high-resolution images across millions of kilometres takes time and power, so images are compressed, downsampled, reduced to manageable file sizes that can be sent back to Earth within reasonable timeframes. Detail is lost in that compression. Structure smooths out, edges blur. Sensor binning exacerbates the problem. To reduce noise in faint targets, spacecraft cameras combine adjacent pixels into superpixels, sacrificing resolution for sensitivity. A 2x2 bin turns 4 pixels into 1, quadrupling brightness but halving resolution in each dimension. For dim comets at the edge of detection, binning is necessary, but it's a devil's bargain. You see the object, but you lose the fine structure, the very details that might reveal whether you're looking at a random ice ball or something far stranger. Amateur astronomers don't face these constraints. They can afford to take thousands of unbinned exposures over hours or even entire nights. They can stack them with sophisticated algorithms that align subpixel features, teasing out details that single exposures can't resolve. Anti-aliasing smoothing, a standard post-processing step in professional astronomy, rounds off sharp edges to prevent false features from appearing in published images. It's a conservative approach, born from decades of embarrassing retractions where apparent structures turned out to be instrumental artifacts. Better to err on the side of caution, to show a smooth, slightly blurry image than to present false details that mislead the public and scientific community. But what if the details aren't false? What if the sharp edges, the geometric patterns, the toroidal structures are real, and smoothing algorithms are erasing the very information we need to understand what we're looking at? That's the nightmare scenario playing out with 3I-ATLAS. Institutional caution is hiding the truth. Conspiracy theories flourished in the gap between amateur and professional imagery. Online forums buzzed with accusations that NASA was intentionally suppressing detail, that agencies worldwide had agreed to downplay the strangeness of 3I-ATLAS to prevent public panic. The reasoning went like this. If an interstellar object exhibits signs of artificiality, revealing that to the public could trigger chaos, religious upheaval, stock market crashes, mass hysteria. Better to show a blurry comet, let the public assume it's natural, and handle the implications behind closed doors. It's a seductive narrative, appealing to our distrust of institutions and our hunger for hidden knowledge. But it's almost certainly wrong. The counter-arguments are mundane but compelling. Governments can't keep secrets that well. Too many people are involved, too many independent observatories, too many international collaborations, too many amateur astronomers with their own equipment. If NASA explicitly told researchers to hide structural details, someone would leak it within weeks. Conspiracy requires coordination, and coordination across hundreds of institutions spanning dozens of countries is functionally impossible. The more likely explanation is boring. Space agencies prioritize different science objectives. They're looking at spectra, measuring composition, tracking trajectories. Morphology, the shape of the coma, is secondary to understanding what the object is made of and where it came from. So they don't spend computational resources on high-resolution imaging. They leave that to the amateurs. But even accepting the mundane explanation, a troubling question remains. Why are multiple independent amateurs capturing the same geometric structures? If it were artifacts, you'd expect variation, different patterns from different processing pipelines, different optical systems. Instead, you get consistency. The 4-point star appears in images processed with PixInsight, with Deep Sky Stacker, with custom Python scripts. The blue halo shows up in data from CMOS cameras, CCD cameras, even modified DSLR cameras. The toroidal morphology is visible in images from the Northern Hemisphere and Southern Hemisphere, captured on different nights under different atmospheric conditions. This level of consistency is the hallmark of a real feature, not a processing glitch. Historical precedent supports the idea that amateurs can see things professionals miss. In 1994, amateur astronomer Alan Hale co-discovered Comet Hale-Bopp, which went on to become one of the most studied comets in history. In 2009, an amateur astronomer in Australia captured an impact event on Jupiter that professional observatories had missed. In 2019, amateurs discovered a massive storm eruption on Saturn before any professional telescope noticed it. Amateurs have time, flexibility, and motivation that professional surveys lack. They watch the same patch of sky night after night. They process data with obsessive attention to detail. They share findings instantly on forums, crowdsourcing analysis in ways that traditional academia can't match. The wavelength question adds another layer. NASA's spacecraft instruments often observe in infrared or ultraviolet, wavelengths invisible to human eyes, but crucial for understanding composition and temperature. Amateurs mostly work in visible light, the wavelengths our eyes evolved to see. It's possible that 3I-ATLAS looks fundamentally different depending on what wavelength you observe it in. The blue halo, prominent in visible light, might be absent or diffuse in infrared. The geometric structure might only manifest in specific emission lines that amateur filters happen to capture while spacecraft instruments miss. This would explain the discrepancy without invoking conspiracy or incompetence. Different tools see different things. Yet even granting that explanation, the core mystery persists. Visible light is arguably the most important wavelength for understanding morphology. It's what we see. It's what cameras capture most easily. If 3I-ATLAS exhibits organized geometry in visible light, that's significant regardless of what it looks like in infrared or ultraviolet. Shape matters. Structure matters. And the structure amateurs are capturing suggests organization that shouldn't exist in a natural comet. So we're left with an uncomfortable possibility. Maybe NASA's blur isn't hiding anything deliberately. Maybe the agencies are genuinely just looking at the object differently, prioritizing different data. But the result is the same. The public sees smooth, featureless images from official sources, while independent researchers resolve geometry that challenges our understanding of what comets can be. And in that gap, that space between institutional caution and amateur discovery, the truth about 3I-ATLAS lurks, unresolved and increasingly urgent. Because if the object looks different depending on who's looking, maybe the strangeness isn't in the data, maybe it's in the object itself. Part 5. The possibility no one wanted to say out loud. Powering up is a dangerous phrase to use in astronomy. It implies intention, agency, decision-making, terms we reserve for living things or engineered systems. Comets don't power up. They heat up. They brighten passively as solar radiation vaporizes their surfaces. The process is thermodynamic, governed by physics, not choice. Yet watching the brightness curve of 3I-ATLAS over November 2025, it's hard to find another phrase that fits. The object wasn't just getting brighter. It was behaving like a system coming online. Coherence increasing, structure tightening, geometry sharpening as if something inside was waking up after a long cold sleep through interstellar space. The brightness spikes told a story that violated standard cometry models. On November 22nd, 3I-ATLAS brightened by approximately 0.7 magnitudes over 12 hours, a surge not correlated with perihelion approach. It was still over 2 astronomical units from the Sun, far enough that solar heating should have been relatively constant day to day. Comets at that distance brighten gradually, smoothly, their light curves predictable within tight margins. Atlas spiked. Then it settled. Then, on November 26th, it spiked again, this time by nearly a full magnitude over 18 hours. These weren't outburst events, which would show rapid brightening followed by exponential decay as ejected material dispersed. These were plateaus, sustained brightness increases that lasted days, as if energy was being channeled more efficiently, concentrated into the core rather than dissipated into a sprawling coma. Typical comets get messier as they approach the Sun. Increased heating vaporizes more ice, expands the coma, creates additional jets from newly activated surface regions. The result is a chaotic, diffuse cloud that grows larger but less organized. 3I-ATLAS did the opposite. As it brightened, its coma tightened. The halo contracted. The toroidal structure became more defined, not less. It was as if the object was consolidating, pulling itself together, organizing its energy output into coherent patterns rather than allowing it to scatter randomly. That's not passive thermodynamic behavior. That's active regulation, the kind of thing you'd see in a system with feedback loops and control mechanisms. Thermal annealing, a process where heat smooths out surface irregularities, has been proposed as a natural explanation. As comets heat up, softer ices sublimate preferentially, leaving behind harder, more refractory materials that form smoother surfaces. A smoother surface reflects light more uniformly, potentially creating the appearance of symmetry. It's an elegant hypothesis. It's also insufficient. Thermal annealing can't produce 94% bilateral symmetry. It can't create 4-point plasma stars. It can't collapse a tail into a toroidal ring. Annealing is a surface process. The structures we're observing involve the entire coma, the 3-dimensional cloud of gas and dust surrounding the nucleus. You can't anneal gas. You can't smooth plasma. The organisation has to come from forces acting on the material after it leaves the surface. Historical comets provide instructive comparisons. Comet Linear C 1999 S4 fragmented spectacularly in July 2000, breaking into dozens of pieces as it approached the Sun. The fragments showed increasing chaos, not coherence. Comet Neowise C 2020 F3 brightened predictably during its 2020 apparition, its coma expanding and diffusing as expected. Comet Shoemaker-Levy 9 famously broke into over 20 fragments before impacting Jupiter in 1994, each fragment behaving independently, chaotically. The pattern is clear. Comets under stress fall apart. They don't organise, they don't tighten, they don't show increasing symmetry. Yet here's 3I-ATLAS, subjected to solar heating, subjected to tidal forces, subjected to radiation pressure, and instead of fragmenting or diffusing, it's becoming more structured. The concept of coherence increase appears in plasma physics and magnetic confinement research. Certain plasma configurations become more stable under specific energy conditions. Tokamaks, the toroidal fusion reactors, achieve stable plasma confinement when temperatures reach critical thresholds. Below that threshold, the plasma is turbulent, chaotic, lossy. Above it, magnetic fields lock the plasma into organised shapes, sustaining the confinement for extended periods. The parallel to 3I-ATLAS is uncomfortable but unavoidable. If the object's coma is partially ionised, and if there's a magnetic field present, then increased solar heating could ionise more material, strengthening the magnetic coupling, creating a positive feedback loop where more energy leads to better organisation. It's speculative, but it fits the data better than any passive model. The tightening of the halo observed from November 20th through November 28th suggests energy concentration. In engineering terms, you'd call it collimation, the process of focusing diffuse energy into a directed beam or compact volume. Flashlights collimate light using reflectors. Lasers collimate photons using resonant cavities. Magnetic nozzles collimate plasma using shaped magnetic fields. If 3I-ATLAS is collimating its coma, deliberately or through some natural but poorly understood process, it would appear exactly as observed. A shrinking, brightening core with a tightly confined halo. The question is whether such collimation can occur naturally in a comet. The answer, based on every comet we've studied in detail, is no. Which leaves us facing the possibility that 3I-ATLAS isn't behaving naturally. This is where the conversation becomes dangerous. Suggesting a comet might be engineered invites immediate ridicule from the scientific community and immediate credulity from the fringe. It's a no-win proposition. But ignoring the data because it points toward uncomfortable conclusions is intellectually dishonest. Science is supposed to follow evidence, not comfort. And the evidence, piling up night after night in amateur images and spectroscopic data, suggests 3I-ATLAS is doing things comets don't do. It maintains symmetry. It confines its coma. It spikes in brightness independently of solar heating. It collapses its tail. If we observe these behaviours in isolation, each could be dismissed as a rare but natural anomaly. Observing them together, in the same object, over sustained periods strains the boundaries of coincidence. The final piece of Act 1's puzzle is a simple, terrifying observation. As 3I-ATLAS moves deeper into the inner solar system, its behaviour isn't decaying toward normalcy, it's escalating. The geometry isn't softening, it's sharpening. The glow isn't dimming, it's intensifying. Whatever is happening to this object, it's accelerating, building towards some threshold or transition we can't yet predict. If Atlas were just an unusually symmetric comet, we'd expect its strangeness to fade as better data revealed prosaic explanations. Instead, every new observation deepens the mystery. And that pattern, that escalation of anomaly, is exactly what you'd expect from a system that's not broken but activating, coming online, preparing for whatever comes next. Act 2 will take us into the physics, the speculation, the uncomfortable parallels between what we observe and what we design if we were engineering an interstellar craft. But before we descend into those depths, remember this. 2 amateur astronomers, working independently, captured images that challenge a century of cometary science, and they did it with backyard telescopes while the institution slept. Part 6. The rotation paradox. Rotation might explain everything, or it might explain nothing. The hypothesis proposed by researchers attempting to reconcile the symmetry with natural phenomena goes like this. If 3I-ATLAS is spinning rapidly enough, the coma averages out into apparent uniformity. Individual jets, asymmetries, and irregularities blur together like the spokes of a spinning wheel, creating the illusion of a symmetric, organized structure. It's an appealing explanation because it invokes only known physics, requires no exotic materials, and makes testable predictions. The problem is that when you run the numbers, the hypothesis collapses under its own implications. To achieve the observed symmetry, ATLAS would need to spin so fast that it should have torn itself apart days ago. Rotational breakup is a well-understood limit in celestial mechanics. Every object has a critical rotation rate beyond which centrifugal forces exceed the self-gravity holding it together. For a rubble pile comet, essentially a loosely bound collection of ice and rock chunks held together by weak gravity and friction, that critical rate is low. Most comets rotate with periods measured in hours or days. A few rotate faster, with periods under 6 hours, but those are typically small, dense objects. The fastest rotating comet on record, P2013-P5, spins with a period of about 3.5 hours, and even it shows signs of shedding material from its equator. For 3I-ATLAS to smooth its coma through rotation, it would need a period under an hour, possibly under 30 minutes. At that speed, a loosely bound comet would explode, fragments flying off tangentially like water droplets from a spinning basketball. The mathematics is straightforward. Centrifugal acceleration at the equator must remain below the surface gravity, or material lifts off. For a 1 kilometre radius comet with typical density around 500 kilograms per cubic metre, self-gravity is feeble, only about 1/10 of a millimetre per second squared. Even modest rotation generates accelerations exceeding that. A 10-minute rotation period produces equatorial acceleration around 1 millimetre per second squared, 10 times stronger than gravity. The comet doesn't hold together. It sheds mass continuously, forming debris clouds, secondary nuclei, and irregular jets. Yet 3I-ATLAS shows none of these features. Its nucleus appears intact. Its coma, though toroidal, doesn't show the spray patterns characteristic of a fragmenting body. This is the rotation paradox. To create the symmetry, it must spin fast. To survive the spin, it must be strong. But comets aren't strong. Angular momentum considerations deepen the paradox. Interstellar objects typically have low rotation rates because the gravitational interactions that eject them from their home star systems tend to dampen rotation. As a planet or star gravitationally slingshots an object into interstellar space, tidal forces can spin it up or down, but the net effect over millions of years is usually slow rotation. Collisions in the Oort cloud or Kuiper belt equivalents of other star systems can impart spin, but those collisions also tend to fracture objects, creating rubble piles even less capable of sustaining high rotation. So for 3I-ATLAS to arrive in our solar system spinning rapidly, something unusual must have happened during its ejection or journey. Either it was spun up by a mechanism we don't understand, or it was launched with high rotation and has somehow maintained it across light years of travel. Toroidal coma smoothing adds another layer of complexity. If you model the coma as a rotating torus of gas and dust, the shape stability depends on the balance between rotational inertia and dispersive forces. Solar wind tries to push material radially outward, away from the sun. Rotation tries to fling material tangentially. For the torus to maintain its shape over days, these forces must balance precisely, which requires either incredible luck or active stabilization. In fluid dynamics, rotating toroidal structures can be metastable, meaning they persist for limited times before turbulence breaks them apart. But cometary comae aren't simple fluids. They're collisionless plasmas mixed with dust grains, subject to electromagnetic forces, radiation pressure, and gravity simultaneously. Stabilizing such a system through rotation alone is like balancing a pencil on its point while riding a unicycle. Possible in theory, implausible in practice. Some researchers have proposed magnetic stabilization as a solution to the rotation paradox. If 3I-ATLAS has an intrinsic magnetic field, it could confine ionized gas into organized structures without requiring extreme rotation. Magnetic fields can do remarkable things to plasma. They can trap it, guide it, shape it into configurations that gravity alone could never maintain. Earth's magnetosphere traps solar wind particles in belts around the planet. Jupiter's magnetic field creates massive plasma toroids around its moons. If ATLAS has even a modest magnetic field, say a few tens of nanoteslas, it could organise its ionized coma into the observed toroidal geometry. The catch is that comets don't generate magnetic fields. They're geologically dead. No core dynamos, no internal heat, no mechanism to sustain magnetic fields over geological timescales. Unless, of course, the field isn't generated internally, but induced by external currents, or carried as remnant magnetism in an unusually metal-rich nucleus. Magnetic confinement in laboratory settings such as tokamaks and stellarators relies on external coils to generate carefully shaped magnetic fields. The plasma never touches the walls of the container because the fields push it back, confining it in a stable configuration. The toroidal shape is particularly favoured because it minimises energy, allowing the plasma to circulate indefinitely without dispersing. If you squint, the resemblance to 3I-ATLAS's coma is uncanny, a glowing torus of ionised gas, confined by magnetic fields, rotating to maintain stability. The difference is that tokamaks are engineered devices with megawatts of power and precisely controlled magnetic coils. ATLAS is supposed to be a natural object, yet the morphology matches, the stability matches, the symmetry matches. It's as if someone built a tokamak and threw it into interstellar space. This paradox, the spin rates that should tear it apart and the cohesion that somehow keeps it together, sits at the centre of the ATLAS mystery. Every conventional explanation requires violating at least one physical constraint. Rapid rotation explains symmetry but demands impossible strength. Magnetic confinement explains stability but requires fields comets shouldn't have. Thermal processes explain brightening but can't account for organisation. We're left juggling impossibilities, trying to find a combination that violates physics the least. And increasingly, the least violated model is one that invokes active systems, feedback mechanisms, and energy management far beyond what passive ice balls can achieve. The rotation paradox isn't just a problem to solve, it's a signpost pointing toward explanations we'd rather not consider. Because if ATLAS isn't spinning impossibly fast, and if it isn't impossibly strong, then the symmetry and stability must come from something else. Something that monitors, adjusts and maintains. Something that behaves less like geology and more like engineering. Part 7. Plasma sheaths, magnetic tori and the artificial-looking glow. The blue glow haunts every image. It's not the warm yellow-white of reflected sunlight, or the green tint of diatomic carbon common in comets. It's a distinct electric blue, the colour of ionised gas energised by processes more intense than simple solar heating. Spectroscopic analysis points toward ionised carbon monoxide, CO+, a common constituent in comet comae formed when ultraviolet light strips electrons from CO molecules. That part is normal. What isn't normal is the intensity, the uniformity, and the spatial distribution of that glow. It hugs the nucleus too tightly, glows too evenly, and persists too consistently to match models of chaotic sublimation. It looks designed, and that resemblance to engineered plasma systems is not just superficial. Plasma sheaths form when ionised gas interacts with a surface or field boundary. Around spacecraft in Earth orbit, plasma sheaths develop as the vehicle's electrically conductive hull interacts with the ionosphere. Electrons and ions accumulate or deplete near the surface, creating a thin layer where electric fields shape particle motion. These sheaths are typically only micrometers to centimeters thick, but they affect everything from radio communication to drag. Scale that concept up. Imagine an object moving through space at interstellar velocities, ploughing through ionized hydrogen, microdust and magnetic field lines. The interaction creates a bow shock, a compressed region ahead of the object, and potentially a trailing plasma sheath. If the object has any electrical conductivity or carries remnant charge, the sheath could organize into observable structures. This is natural and expected. But the geometry we observe in 3I-ATLAS goes beyond simple bow shocks. It shows toroidal symmetry, tight confinement, and stability over days. That requires more than passive interaction. Magnetic tori, donut-shaped plasma structures confined by magnetic fields, are the workhorses of fusion research. A tokamak generates toroidal magnetic fields using external coils, then induces a current in the plasma itself, creating a secondary poloidal field. The combination twists magnetic field lines into helical paths that trap plasma away from the reactor walls. Stellarators achieve similar confinement using twisted coils without relying on plasma current. Both designs aim for the same goal: keep million-degree plasma stable long enough for fusion reactions to occur. The toroidal shape minimizes energy, allowing the system to persist without rapidly dissipating. And visually, from certain angles, these laboratory plasmas look eerily similar to the blue halo surrounding 3I-ATLAS. Same shape, same glow, same tight confinement. The solar wind shapes cometry come, but usually into elongated teardrops, not toroids. Magnetic field lines in the solar wind can drape around a comet, creating current sheets and plasma boundaries, but these structures are typically asymmetric, distorted by the comet's motion and the uneven distribution of outgassing. To create a symmetric torus, you need either an axially symmetric outgassing pattern, which is improbable given the irregular shape of comet nuclei, or a confining field that overwhelms local asymmetries. Planetary magnetospheres achieve this through strong intrinsic fields. Io, Jupiter's volcanic moon, is embedded in Jupiter's powerful magnetic field, which traps sulfur and oxygen ions from Io's volcanoes in a massive plasma torus orbiting Jupiter. The Io plasma torus is one of the most prominent toroidal structures in the solar system, and it exists because of external magnetic confinement. If 3I-ATLAS were embedded in a strong local magnetic field, either intrinsic or induced, it could theoretically create a miniature version of the Io torus. But where would such a field come from? Controlled ionization offers a speculative but fascinating mechanism. In spacecraft engineering, plasma contactors deliberately ionize gas to control electrical potential, reducing charge buildup that could damage electronics. Electric propulsion systems like Hall thrusters ionize propellant and accelerate it using electric and magnetic fields generating thrust. If a spacecraft were traveling at high speeds through interstellar medium, it might intentionally create a plasma bubble around itself, using controlled ionization and magnetic shaping to deflect microdust and charged particles. The bubble would glow, emitting light from recombination and excitation processes, and from certain angles it would appear as a symmetric halo around the craft. The resemblance to 3I-ATLAS's blue glow is uncomfortable because it suggests functionality. The glow isn't waste, it's operational. Solar magnetic field lines interacting with a charged or magnetic object create complex dynamic structures. Earth's magnetosphere is constantly buffeted by solar wind, compressing on the sunward side and stretching into a long magneto-tail on the night side. During geomagnetic storms, reconnection events inject energy into the magnetosphere, causing auroras, radiation belt enhancements, and other dynamic phenomena. If 3I-ATLAS has any magnetic moment, even a weak one, the Sun's magnetic field could interact with it, organizing the coma plasma into structures more stable than random outgassing would produce. This is a natural process, observed in principle around magnetized asteroids, and potentially some comets. But the level of organization in Atlas's coma exceeds what we've seen elsewhere, suggesting either an unusually strong magnetic interaction or something more deliberate. Speculating about protective bubbles ventures into science fiction, but it's grounded in real physics. High-speed travel through even the tenuous interstellar medium poses risks. At 10% the speed of light, a collision with a grain of dust releases energy equivalent to a hand grenade. Over decades or centuries of travel, countless such impacts would erode any surface, pitting and scarring it beyond recognition. One proposed solution, explored in theoretical studies of interstellar ramjet designs, is to generate a magnetic or plasma bubble ahead of the spacecraft, deflecting particles before they can impact the hull. The bubble doesn't need to be solid, just conductive enough to divert charged particles and ionize incoming neutrals so they can be magnetically pushed aside. Such a bubble would glow from the energy dissipated in ionization and deflection. It would be symmetric if the magnetic field generating it was symmetric, and it would be tight, close to the spacecraft to minimize energy requirements, exactly as we observe in 3I-ATLAS. Natural plasma structures provide important context. Earth's magnetosphere, as mentioned, is a protective bubble. Auroras are visible manifestations of plasma dynamics, glowing curtains of ionized gas energized by magnetic reconnection. Solar coronal loops, enormous arcs of plasma following magnetic field lines, demonstrate that magnetic confinement can create stable, long-lasting structures on massive scales. Comets themselves generate ion tails, streams of ionized gas that glow blue from CO+ and other ions. All of these are natural. None of them are toroidal, symmetric, and tightly confined in the way ATLAS coma appears. Nature can create plasma structures, but the specific geometry we observe is rare, requiring conditions that don't typically coexist in comets. The smoothness and symmetry stand out, not as impossible, but as improbable enough to demand alternative explanations. The difference between natural and engineered plasma structures often comes down to stability and symmetry. Natural structures are messy, dynamic, shaped by turbulent interactions and chaotic initial conditions. Engineered structures are smooth, stable, designed to minimize energy dissipation and maximize confinement time. When you compare images of tokamak plasmas with images of 3I-ATLAS's halo, the resemblance isn't perfect, but it's closer than the resemblance between ATLAS and any natural comet. That doesn't prove anything. Resemblance isn't evidence, but it's suggestive, and when combined with the rotation paradox, the vanishing tail, and the brightness spikes, the cumulative weight of these observations pushes toward a conclusion that feels both inevitable and absurd. Either we're watching the most anomalous natural comet in recorded history, or we're watching something that was engineered to look like a comet while performing functions comets don't perform. The glow, the halo, the toroidal symmetry, they're not just pretty, they might be functional, and that possibility, however uncomfortable, refuses to go away. Part 8. The Intelligence Hypothesis. Let's set boundaries immediately. This is not about declaring 3I-ATLAS an alien spacecraft. This is about exploring what an engineered interstellar object would need to do to survive the journey between stars, and noticing uncomfortably that ATLAS exhibits several behaviours consistent with those engineering requirements. We're not claiming proof. We're asking what engineering logic would demand if such a craft existed, and observing that the anomalies we've documented align with that logic more closely than they align with natural cometary behaviour. This is speculative astrophysics meeting engineering analysis, and it's important to state clearly, we're not scientists making claims. We're observers asking uncomfortable questions. An interstellar craft, travelling for thousands or millions of years between star systems, faces survival challenges that dwarf anything in our solar system. Cosmic dust, though sparse, becomes a sandblaster at interstellar velocities. A grain of sand impacting at 10% light speed carries kinetic energy equivalent to a car crash. Over millennia, countless such impacts would ablate any exposed surface, eroding it down to nothing unless protected. Whipple shields, the multi-layered bumpers used on spacecraft like the International Space Station, work by vaporizing incoming particles in outer layers, dissipating energy before it reaches critical systems. But Whipple shields are passive. They degrade with each impact. For journeys lasting geological timescales, active protection might be necessary. Plasma shields represent one speculative approach to active protection. By generating a magnetic field and ionizing gas ahead of the craft, incoming particles could be deflected or slowed before impact. The concept appears in various theoretical propulsion studies, including Bussard ramjet designs, where a magnetic scoop collects interstellar hydrogen for fuel. The same magnetic field that collects fuel also deflects dangerous particles, creating a protective cocoon around the spacecraft. Such a shield would glow, emitting light from the energy transferred to deflected particles. It would be roughly symmetric if the magnetic field generating it was symmetric, and it would be essential for long-duration travel through the interstellar medium, where even low particle densities become hazardous at relativistic or near-relativistic speeds. Radiation poses another existential threat. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent events, permeate interstellar space. Over decades or centuries, accumulated radiation dose would destroy electronics, degrade materials, and, if the craft carried any biological components, sterilize or mutate them beyond functionality. Earth's magnetosphere shields us from most cosmic rays. Mars, with no global magnetic field, receives far higher doses. An interstellar craft needs similar protection, either through thick shielding, which adds mass and cost, or through magnetic deflection, which adds complexity but saves mass. A magnetic bubble capable of deflecting charged particles would, again, produce a glowing plasma sheath, visible from outside as a symmetric halo. The parallels to ATLAS's blue glow become harder to dismiss. Magnetic storms, fluctuations in the interstellar magnetic field, caused by turbulence or proximity to stellar wind boundaries, could induce currents in a conducting craft, potentially damaging systems or altering trajectory. Active magnetic management, using onboard field generators to counteract or exploit external fields, might be necessary for navigation and protection. Such systems would dynamically adjust field strength and orientation, possibly producing observable changes in plasma configuration. If 3I-ATLAS is actively managing a magnetic bubble, we might expect brightness fluctuations, geometry changes, or toroidal reshaping as it responds to changing interstellar conditions, or its entry into the Sun's magnetic domain. And that's exactly what we observe: brightness spikes, coma tightening, tail collapse. Behaviors consistent with active regulation. Rotational stabilization is fundamental to spacecraft design. Without active control, spacecraft tumble chaotically due to asymmetric outgassing, solar radiation pressure, or micro-impacts. Spin stabilization, rotating the craft around a single axis, provides stability without requiring active thrusters. Satellites like Tyros and many early spacecraft used spin stabilization for this reason. But spin must be carefully controlled. Too fast, and the craft risks structural failure. Too slow, and it loses stability. For an interstellar craft, spin serves another purpose: averaging. If the craft rotates rapidly, any asymmetric heating, radiation exposure, or particle impacts get distributed evenly over the surface, preventing localized degradation. This is rotational averaging, and it naturally produces symmetric external signatures. A rotating craft surrounded by a plasma bubble would appear, from a distance, as a symmetric glowing object, exactly as 3I-ATLAS appears. Energy blooming, using stars as recharge points or navigation waypoints, is entirely speculative but conceptually plausible. If a craft is powered by solar panels, radioisotope generators, or any system that degrades over time, it might plan its trajectory to pass near stars, using solar radiation for power replenishment. As it approaches a star, systems that were dormant or operating at minimal power could activate, brightening the craft's electromagnetic signature. Atlas's brightness spikes, not correlated with perihelion, could fit this pattern if the object is powering up systems in response to increasing solar energy availability. It's a hypothesis that explains the timing of the brightness increases better than sublimation models do. We observe coherence, the maintenance of organized structure over time. We observe symmetry, the alignment of features with geometric precision. We observe brightness modulation, changes in luminosity not predicted by passive heating. These are all features you'd expect from a controlled system responding to environmental conditions. They're not proof of engineering, but they're suggestive of it. And when you place them alongside the historical mystery of 1I Oumuamua, with its unexplained non-gravitational acceleration and complete lack of visible outgassing, a pattern emerges. Two interstellar objects, both exhibiting behaviors that strain natural explanations. Oumuamua accelerated without visible jets. Atlas organizes its coma without apparent cause. Either we're incredibly unlucky, encountering the two strangest natural objects in recorded history within 8 years of each other, or we're encountering something that was never natural to begin with. The intelligence hypothesis doesn't require biology or consciousness. It requires only engineering, the application of physical principles to achieve specific outcomes. A probe, launched millions of years ago by a civilization long extinct, could still function, executing pre-programmed instructions, maintaining its systems, navigating towards stars as waypoints or destinations. It wouldn't think, it wouldn't communicate, it would just operate, following the logic burned into its circuits or whatever passes for memory in its design. And to us, observing it from a distance, it would look strange, organized, purposeful, not because it's alive, but because it's functional. The question isn't whether 3I-ATLAS is intelligent. The question is whether it's engineered, and increasingly the anomalies suggest that if it is just a comet, it's the unluckiest comet in the universe, exhibiting every trait that would make us suspect artificiality without quite crossing the threshold into undeniable proof. Or maybe it's not unlucky. Maybe it's exactly what it looks like. Part 9. The Data Suppression Debate. Institutional imaging of fast-moving objects involves compromises that create systematic blur. When a spacecraft photographs a comet from thousands of kilometers away, while both are in motion relative to each other, The effective exposure time must be short enough to prevent smearing, but short exposures capture less light, reducing signal-to-noise ratio for faint targets. The solution is frame averaging. Take multiple short exposures and sum them together, boosting signal while averaging out random noise. This works well if the target is stationary relative to the frame, but if it's moving, even slightly, each frame captures it at a different pixel location. Aligning and stacking moving targets requires sophisticated algorithms that estimate motion, shift frames to compensate, and blend them seamlessly. Small errors in motion estimation accumulate, blurring fine details. Professional spacecraft do this automatically, but the algorithms prioritize robustness over resolution. They'd rather produce a smooth, slightly fuzzy image than a sharp image with artifacts. The result is systematic loss of detail. Sensor binning combines adjacent pixels into superpixels before readout, reducing data volume and increasing sensitivity at the cost of resolution. A 2x2 bin turns a 4 megapixel image into a 1 megapixel image, quartering file size and quartering noise per superpixel. For faint comets at the detection limit, binning is often mandatory. Without it, the signal drowns in noise, and you see nothing. With it, you see something, but details vanish. Edges blur. Structure smooths into gradients. A symmetric 4-point star might become a slightly elongated blob. A toroidal ring might become a fuzzy circle with no hole. Binning doesn't hide details maliciously. It erases them mathematically, irreversibly, before the data is even stored. You can't recover binned detail later. It's gone. And for most scientific purposes, that's acceptable, because researchers care more about brightness, colour, and spectral composition than morphology. But for objects like ATLAS, where morphology might be the most important clue, binning becomes a barrier to understanding. Anti-aliasing smoothing prevents false features by rounding off sharp edges in images. When you digitize a circular object onto a square pixel grid, the edge becomes jagged, a staircase of pixel transitions. Anti-aliasing smooths those transitions, interpolating between pixels to create visually cleaner edges. It's standard practice in image processing, preventing the publication of spurious patterns that result from pixelation rather than real structure. But it's a double-edged sword. If the object genuinely has sharp features, geometric edges, or structured light distribution, anti-aliasing softens those features, making engineered geometry look more natural. For 3I-ATLAS, if the plasma star and toroidal ring are real, sharp-edged structures, anti-aliasing would blur them, making them appear like natural comets. Amateurs, processing their own data with less conservative settings, might skip aggressive smoothing, preserving the sharp details professionals erase. This explains the discrepancy, without invoking conspiracy. Different processing philosophies produce different results. The conspiracy angle argues that NASA and other agencies intentionally hide detail to prevent public alarm. Proponents point to classified programs, historical cover-ups like the Tuskegee syphilis study or MKUltra, and the general secrecy surrounding aerospace projects. If an interstellar object showed signs of artificiality, the reasoning goes, revealing that to the public could destabilize societies. Religious institutions might fracture. Governments might face demands for transparency they can't or won't meet. Stock markets could crash on uncertainty. Better, from a governmental perspective, to quietly study the object, prepare contingency plans, and release sanitized imagery that reassures the public while specialists work behind the scenes. It's a narrative that fits our cynicism about institutions, our distrust of authority, our hunger for hidden truths. The counter-arguments are practical and compelling. Secrets of this magnitude don't stay secret. Too many people are involved. Multiple space agencies across competing nations, dozens of ground-based observatories, thousands of professional and amateur astronomers worldwide. Coordination across that scale is functionally impossible. Someone talks, someone leaks. The history of whistleblowing demonstrates that individuals prioritize truth over institutional loyalty when the stakes are high enough. If astronomers worldwide were ordered to suppress evidence of extraterrestrial artifacts, the leaks would begin within days, not years. Conspiracy requires coordination, and coordination at global scale with perfect fidelity is a fantasy. The mundane explanation, that space agencies process data conservatively and prioritize different science questions, is far more plausible. Bandwidth constraints are real and severe. Spacecraft transmit data across millions or billions of kilometers using radio signals that take minutes to hours to arrive. Transmission rates are measured in kilobits per second, agonizingly slow by modern internet standards. High-resolution images are megabytes or gigabytes in size. Sending them takes hours per image, and spacecraft have limited power budgets, finite antenna pointing time, and packed science schedules. So images are compressed, downsampled and prioritized. Only the most scientifically valuable data gets transmitted in high resolution. Morphology, unless it's the primary science objective, takes a backseat to spectroscopy, photometry, and trajectory refinement. This explains why amateur images might be sharper than official releases. Amateurs don't face bandwidth limits. They process data locally, at full resolution, with unlimited computational resources and time. The discrepancy is expected, not suspicious. Raw data complexity poses another barrier. Spacecraft images arrive as raw sensor data, uncalibrated, uncorrected for optical distortions, contaminated by cosmic rays and instrumental noise. Processing raw data into publishable images requires expertise, specialized software, and decisions about color mapping, contrast enhancement, and artifact removal. Different choices produce different images, all technically valid but visually distinct. NASA releases processed images that balance scientific accuracy with public accessibility, avoiding enhancements that might create false features or mislead non-experts. Amateurs processing the same raw data or their own observations might choose aggressive enhancements that reveal subtle details but also risk introducing artifacts. The fact that multiple amateurs independently see the same features suggests those features are real, but institutional caution prevents official confirmation until exhaustive verification is complete. Anti-overprocessing caution is a learned response to historical embarrassments. Astronomy has a history of false discoveries where processing artifacts were mistaken for real phenomena. The famous Face on Mars, captured by Viking 1 in 1976, appeared to show a structured face-like feature in Cydonia. Later, high-resolution images revealed it as a natural mesa, the face-like appearance an artifact of lighting angle and low resolution. Pulsar planets, announced in 1992, were later attributed to timing errors in data processing. These errors taught astronomers to be conservative, to under-enhance rather than over-enhance, to present data that might be less exciting but is less likely to mislead. That conservatism protects scientific credibility, but can suppress real anomalies if they're subtle enough to be mistaken for noise. Wavelength differences add another layer. NASA's spacecraft often observe in infrared, detecting heat rather than visible light. Infrared reveals composition and temperature, critical for understanding what comets are made of and how they evolve. Visible light, the wavelengths amateurs work in, reveals morphology and structure. If 3I-ATLAS looks different in infrared than in visible light, both observations can be correct without either being misleading. The blue halo, prominent in visible emissions from ionized molecules, might be dim or absent in infrared. The toroidal structure, shaped by magnetic fields affecting ions, might not appear in thermal emissions dominated by dust. This would reconcile the discrepancy. Professionals see one thing, amateurs see another, and both are real, just in different wavelengths. The final uncomfortable possibility is that the discrepancy isn't about human choices at all. Maybe 3I-ATLAS looks different depending on observation method, because the object itself responds to observation. Not consciously, not with awareness, but functionally, the way a chameleon changes colour in response to its environment. If the object has electromagnetic systems that interact with radar, radio, or other active sensing, those systems might alter configuration when pinged, creating different appearances for passive optical observation versus active radio probing. This edges into paranoia, but it's physically plausible for sufficiently advanced engineering. Stealth technology on Earth works this way, absorbing or deflecting radar to minimize detection. An interstellar craft might do similar, presenting a benign cometary appearance to passive observers, while active sensors see something structured. It's wild speculation, unsupported by evidence, but it fits the pattern. Official images show blur, amateur images show geometry, and the disconnect grows with each new observation. Either NASA is hiding detail, or Atlas is hiding itself. And increasingly, the data doesn't let us dismiss either possibility. Part 10. The beacon theory. Brightness pulses, if they're real, change everything. Several amateur observers reported periodic brightness variations in 3I-ATLAS over observation windows spanning November 20th through November 30th, 2025. The variations weren't smooth, sinusoidal modulations typical of rotating objects. They were spikes, rapid increases followed by plateaus and gradual declines, repeating with periods ranging from 6 to 18 hours depending on the observer and analysis method. Extracting periodic signals from noisy photometric data is notoriously difficult. Atmospheric turbulence, cloud passages, and instrument drift all introduce fluctuations that can mimic periodic behavior. But when multiple observers in different locations report similar periods, the signal gains credibility. If the brightness spikes are real, they demand explanation. And the simplest explanation, rotational modulation, doesn't fit the data. The spikes are too sharp, too asymmetric, suggesting episodic events rather than continuous rotation. Rotational brightness variations occur when an irregularly shaped object spins, presenting different surface areas or reflectivity patches to the observer. Asteroids show this behavior constantly. As they rotate, their brightness rises and falls in smooth curves, twice per rotation if the object is elongated, once per rotation if it has a single bright spot. The light curves are predictable, symmetric, easily modelled with basic geometry. 3I-ATLAS's reported brightness spikes don't match that pattern. They're too fast, rising in minutes rather than hours, and they don't show the smooth sinusoidal shape of reflected sunlight from rotating surfaces. They look more like outburst events, sudden releases of energy that briefly increase luminosity before decaying. But outbursts are random, triggered by internal stress or heating, not periodic. The periodicity suggests intention, or at least systematic cause. The beacon theory proposes that the brightness spikes serve a navigational or communicative function. Imagine a lighthouse rotating its beam across the ocean. To a distant ship, the light appears to flash, periodically as the beam sweeps past. If 3I-ATLAS is emitting directed beams of light or plasma, rotating to sweep those beams through space, observers on Earth would see periodic flashes as the beam aligns with our line of sight. This explains the sharpness and asymmetry. We don't see the object dimming smoothly as it rotates. We see sudden brightening when the beam points at us, followed by gradual fading as the beam sweeps away. The periodicity reflects the rotation rate, while the sharp rise reflects the narrow beam width. It's speculative, but it fits the photometric data better than passive rotation. Pulsars, rotating neutron stars emitting beams of radio waves from their magnetic poles, are natural beacons. As the star rotates, the beam sweeps across space, creating a lighthouse effect visible as periodic radio pulses. Pulsars are some of the most precisely timed objects in the universe, their periods stable to nanoseconds, making them valuable tools for testing general relativity and detecting gravitational waves. If 3I-ATLAS is emitting something similar, not radio waves, but visible or ultraviolet light beamed from specific directions, it would appear as a pulsing light source. The parallel is eerie because pulsars are natural phenomena, yet they resemble engineered timing devices. If ATLAS is doing something similar, it blurs the line between natural and artificial. Oumuamua's tumbling motion and brightness variations, observed during its 2017 passage, were attributed to an elongated, rotating object reflecting sunlight. But the light curve was strange, showing larger than the expected amplitude and irregular variations suggesting a highly elongated, possibly pancake-shaped object. Some researchers proposed it was tumbling chaotically, others that it had a structured shape unlike typical asteroids. The non-gravitational acceleration, attributed to outgassing despite no visible coma, added to the mystery. If Oumuamua was emitting gas directionally, acting like a natural thruster, that would explain the acceleration. But it would also suggest anisotropic, non-random outgassing, hinting at either bizarre geometry or active control. ATLAS's brightness spikes echo that mystery. If the spikes result from directed emissions, gas jets, or plasma beams, they indicate control, intentionality, function. Course correction is one plausible function for directed emissions. Spacecraft use thrusters to adjust trajectory, firing bursts of gas to nudge velocity in desired directions. If an interstellar craft were navigating toward our Sun, using it as a waypoint or destination, It might fire thrusters periodically to refine its approach. Those thruster burns would appear as brightness spikes if the exhaust plume faced Earth. The periodicity would reflect the navigation update schedule, programmed intervals when the craft checks its position and makes corrections. This is pure speculation, unsupported by direct evidence, but it's consistent with the observed behaviour. A navigating object would pulse. A tumbling rock would glow steadily. ATLAS pulses. Environmental mapping offers another function. If the craft is equipped with sensors measuring magnetic fields, particle density or radiation, it might emit pulses to probe the environment, using the reflections or interactions to build a map of local conditions. Active sonar in submarines works this way, emitting sound pulses and analysing echoes. Active radar maps terrain by bouncing radio waves off surfaces. An interstellar craft entering an unfamiliar star system might use similar techniques, emitting pulses of electromagnetic radiation or plasma and analysing what comes back. To distant observers, these pulses would appear as periodic brightness variations, functional rather than aesthetic. The symmetry of Atlas's coma might be functional as well, not an accidental consequence of rotation, but a designed feature. If the glow serves as a protective bubble, shielding the craft from microdust and radiation, then maintaining symmetry ensures uniform protection. Asymmetric shields have weak points, regions where particles could penetrate. Symmetric shields distribute stress evenly, reducing the chance of localized failure. Engineering favors symmetry for this reason. It's robust, predictable, efficient. The fact that Atlas maintains its symmetry over days suggests active regulation. Systems that monitor the shield and adjust field strengths or plasma density to compensate for perturbations. This is spacecraft engineering, not geology. Ancient myths and legends occasionally reference cosmic lighthouses, celestial beacons guiding travellers through the heavens. These are usually dismissed as metaphors or imaginative interpretations of bright stars or planets. But if interstellar travel is possible, if ancient civilizations achieved it, then navigational beacons spanning light years would be necessary infrastructure. Place beacons at strategic points, bright enough to be visible across vast distances, pulsing with identifiable patterns to distinguish them from natural stars. Travellers use them as waypoints, charting courses from beacon to beacon across the galaxy. It's science fiction, but it's also basic navigation logic. If 3I-ATLAS is such a beacon, either automated or carrying a signal, its periodic brightness variations might be its announcement. I am here. Use me, follow me, or avoid me. The theory remains speculative, built on patterns that might be noise, observations that might be artifacts. But it explains more than randomness does. It explains the periodicity, the sharpness, the symmetry, the brightness spikes independent of solar heating. It explains why Atlas behaves like a system rather than a rock. And it opens a possibility both exhilarating and terrifying, that 3I-ATLAS isn't just visiting our solar system. It's navigating through it, using the sun as a reference point, pulsing its presence to whatever other travellers might be watching, executing functions that have nothing to do with us, but that we're privileged or cursed to witness. If it's a beacon, the question becomes, for whom? Who or what is listening for these pulses, and what happens when they arrive? Part 11. November 2025, the solar heliosheet dimpling event. The sun is not a simple sphere of glowing gas. It's a dynamic, violent system threaded with magnetic fields that twist, snap, and reconnect in patterns so complex they challenge our best supercomputers. The heliospheric current sheet, a vast undulating surface where the sun's magnetic field changes polarity, extends billions of kilometers into space, wobbling up and down like a twirling skirt as the sun rotates. The Parker spiral, the shape of magnetic field lines dragged outward by solar wind, creates a galaxy-wide magnetic structure connecting our star to the interstellar medium. Normally, these structures behave predictably, wobbling and shifting, but maintaining overall form. In mid-November 2025, something unusual happened. Solar physicists analysing magnetograph data noticed localized warping in the current sheet, regions where the surface dimpled inward, creating pockets of enhanced magnetic field strength. They called it dimpling, and while not unprecedented, the timing and location were suspicious. Magnetic anomalies affect how solar wind interacts with objects passing through it. Comets, especially active ones shedding gas and dust, develop ion tails shaped by magnetic field lines. When those field lines are disturbed, twisted by magnetic reconnection or compressed by shock waves, comet tails respond, bending, brightening, or disconnecting entirely. The November dimpling event occurred in a region of space 3I-ATLAS was approaching, and observers noted that the toroidal collapse of Atlas's tail coincided temporally with peak dimpling. Correlation isn't causation, but the timing was noteworthy. If Atlas's unusual coma behavior resulted from interaction with local magnetic fields, and if those fields were unusually strong due to dimpling, then the correlation makes physical sense. The comet encountered an environment different from typical interplanetary space, and its plasma responded. Solar field knots, regions where magnetic field lines tangle into complex configurations, are known to exist but poorly understood. They're transient, forming during periods of high solar activity, when coronal mass ejections and flares inject energy into the heliosphere. Within these knots, field strengths can be orders of magnitude higher than surrounding space, creating pockets where charged particles behave differently. If 3I-ATLAS passed through or near a field knot, its ionized coma would experience forces not present elsewhere. Ions would be confined more tightly, organized along magnetic field lines, potentially creating the toroidal structures observed. This is a natural explanation, invoking only solar physics and plasma dynamics. But it requires ATLAS to encounter the knot at precisely the time observers were watching, a coincidence that raises questions. Historical examples demonstrate solar influence on cometary tails. In 1910, Halley's Comet experienced a disconnection event, where its ion tail detached and drifted away, driven by magnetic reconnection in the solar wind. The event was dramatic, captured by photographers worldwide, and demonstrated that comet tails are not static features but dynamic structures responding to changing solar conditions. In 2007, Comet Encke's tail disconnected multiple times during its apparition, each event linked to solar wind disturbances. These are natural, well-documented phenomena, but they produce chaos, not organization. Tails that disconnect don't collapse into symmetric toroids. They shred, disperse, become irregular. Atlas' tail didn't shred. It organized, tightening into a structure more stable after the dimpling event than before. That's the opposite of what solar disturbances typically cause. Plasmatorae near magnetic warps are theoretically expected. When charged particles encounter regions of rapidly changing magnetic field strength, they can become trapped, circulating along field lines in toroidal paths. Earth's radiation belts are examples. Charged particles trapped in the magnetosphere, spiraling along magnetic field lines in donut-shaped regions. If the November dimpling created localized magnetic traps, and if Atlas's coma ions entered those traps, they could be confined into toroidal shapes. This explains the morphology without invoking anything beyond known physics. The catch is that such traps are usually transient, lasting hours to days before solar wind changes dissipate the configuration. Atlas Taurus persisted longer, suggesting either exceptional stability in the magnetic environment or active maintenance by the object itself. Solar storms provide context. During periods of high solar activity, coronal mass ejections blast billions of tons of plasma into space, compressing the magnetic field ahead of them, creating shock waves that ripple through the heliosphere. These storms dramatically alter comet tails, brightening them, disconnecting them, or distorting them into unusual shapes. If the November dimpling event was associated with a minor solar storm, too small to be widely reported but large enough to affect local magnetic topology, it could explain Atlas's behavior. Storm-enhanced magnetic fields would confine plasma more effectively, creating the observed torus. Storm-associated shocks could trigger brightness spikes as the coma compresses and heats. All natural, all explainable. But the timing, the precise alignment of dimpling, Atlas passage, and observer attention strains probability. This event, real in terms of observed solar magnetic disturbances, connects Atlas to broader solar dynamics. It places the comet in context, not as an isolated anomaly, but as an object interacting with a complex variable environment. If Atlas's strange behavior results from environmental factors, from the specific magnetic topology it happened to encounter, then other comets entering similar regions might show similar features. That's testable. Researchers can analyze archival data, searching for other comets that pass through magnetically disturbed regions, checking whether they showed toroidal comae or brightness anomalies. If they did, ATLAS becomes less unique, more explainable. If they didn't, the mystery deepens because it suggests ATLAS responds to magnetic fields differently than other comets, hinting at intrinsic differences in composition, structure, or function. The November solar activity reframed how scientists approach small bodies. Multiple research groups began modelling comet plasma interactions with higher fidelity, incorporating time-varying magnetic fields and reconnection events. Papers submitted to journals in late 2025 referenced ATLAS explicitly, using it as a case study for unusual plasma dynamics. The scientific community, initially skeptical or dismissive, started taking the observations seriously, not because they believed ATLAS was artificial, but because the data demanded explanation. Natural or not, ATLAS was teaching us something about how comets behave in extreme magnetic environments, and in teaching us that, it was also revealing how little we understand about the interstellar medium, the solar wind transition regions, and the complex interplay between magnetic fields and ionized gas in astrophysical contexts. The dimpling event was a wake-up call, a reminder that space is weirder than our models predict. Part 12. Late 2025. The multi-nation push for deep space radar imaging. Radar imaging of asteroids and comets has been a cornerstone of planetary defense and science for decades. By bouncing radio waves off distant objects and analyzing the echoes, astronomers can determine shape, rotation rate, surface roughness, and even composition. Apophis, the asteroid that will pass close to Earth in 2029, has been extensively radar imaged, revealing a peanut-shaped object tumbling through space. Bennu, target of NASA's OSIRIS-REx mission, was radar mapped before the spacecraft arrived, allowing mission planners to predict its rotation and select safe sampling sites. Radar sees through clouds, works day or night, and provides spatial resolution that visible light telescopes can't match for nearby objects. But radar's range is limited. Power falls off with the fourth power of distance, making distant targets extremely difficult to image. Upgrading radar facilities to reach farther, to image objects in the outer solar system and beyond, requires massive investment. In October 2025, funding proposals from NASA, the European Space Agency, and Japan's JAXA suddenly accelerated through bureaucratic channels. Each agency independently requested budget increases for deep space radar capabilities, citing planetary defense needs and scientific curiosity about interstellar objects. The timing raised eyebrows. Budget cycles typically take years. Major infrastructure upgrades require congressional or parliamentary approval, environmental reviews, international coordination. Yet within weeks, funding appeared, contracts were awarded, and construction timelines were fast-tracked. Officially, the push responded to the growing recognition that interstellar objects are more common than previously thought, and that understanding them requires better tools. Unofficially, whispers circulated that 3I-ATLAS was the catalyst. Deep space radar upgrades focus on increasing transmitter power and receiver sensitivity. Current facilities like Arecibo, before its collapse, and the Goldstone Deep Space Network can image objects out to tens of millions of kilometers under ideal conditions. The proposed upgrades aim to double or triple that range, allowing radar imaging of objects in the asteroid belt and potentially even Jupiter's orbit. The technical challenges are immense. Higher power requires larger transmitters, more robust cooling systems, and power plants capable of sustaining megawatt-level output for hours. Higher sensitivity requires larger receivers, better signal processing, and sophisticated algorithms to extract signal from noise. The cost runs into hundreds of millions of dollars per facility, expenditures that demand justification. Speculation about ATLAS driving the urgency centers on classified observations. Some amateur astronomers theorize that space agencies detected features in ATLAS's radar echo, structural details not visible in optical images that prompted concern. Radar can distinguish between solid surfaces and loose rubble, between smooth spheres and faceted polyhedrons. If ATLAS returned a radar echo suggesting artificial geometry, flat surfaces, sharp edges, or reflectivity anomalies inconsistent with natural comet nuclei, that would justify immediate investment in better radar. The problem is that ATLAS is too far for current radar systems to image effectively. By the time upgraded facilities come online in late 2026 or 2027, ATLAS will have passed perihelion and be receding. The window for high-resolution radar imaging is narrow, possibly already closed. That urgency aligns with the scenario where authorities want to characterize this object before it leaves, before the opportunity vanishes for another century or forever. Political urgency for planetary defence provides cover for other motivations. In recent years, governments have taken asteroid threats more seriously, funding surveys, developing deflection technologies, and conducting impact simulations. The proposed radar upgrades fit within that framework, defensible, as prudent investment in humanity's future. But insiders note that the specific language in funding proposals emphasises interstellar objects, not near-Earth asteroids. Interstellar objects pose no collision risk on human timescales. They pass through the solar system once and never return. Spending hundreds of millions to image them makes scientific sense, but doesn't align with planetary defence priorities. Unless, of course, the objects are considered potential threats in ways other than collision. If an interstellar object exhibits behaviour suggesting artificial origin, studying it becomes a matter of security, not just curiosity. Radar's ability to reveal shape and structure makes it the ultimate test for artificiality. A natural comet nucleus is irregular, lumpy, covered with craters and fractures. An engineered spacecraft, even one disguised to resemble a comet, likely has flat surfaces, antennas, or geometric features detectable in high-resolution radar images. If 3I-ATLAS were radar imaged and showed such features, the debate would end. We'd know. The absence of public radar images of ATLAS fuels speculation that either attempts failed due to range limitations or succeeded, and results are classified. Either scenario is plausible. Either scenario is unsettling. Early warning systems for interstellar objects are scientifically justified. We've now detected 3: Oumuamua, Borisov, and ATLAS. Each discovery was accidental, made by surveys designed for other purposes. Dedicated systems optimized to detect fast-moving objects with hyperbolic orbits would give months or years of advance warning, allowing detailed study and, if necessary, response. Radar plays a key role in such systems, providing rapid characterization that optical telescopes can't match. Building that capability now, while public attention is focused on ATLAS, is strategically smart. Whether the motivation is purely scientific or includes security concerns is an open question. Institutional interest that the public doesn't see manifests in conference proceedings, funding shifts, and personnel reassignments. In late 2025, several prominent radio astronomers quietly shifted focus from pulsars or galaxies to solar system radar studies. Job postings appeared for specialists in radar signal processing with security clearances. International collaborations on radar astronomy, previously dormant, reactivated with unusual speed. These are subtle indicators, not smoking guns, but they paint a picture of communities mobilizing around a perceived need. Something triggered urgency. And the timing points to ATLAS. Are institutions seeing something we aren't? Almost certainly. Space agencies have access to data not publicly released, observations from classified military satellites, radar echoes from facilities that don't publish results, spectroscopic measurements taken by instruments whose very existence is secret. If any of those sources revealed anomalies in ATLAS structure or behaviour, the information would be tightly controlled, shared only with officials holding appropriate clearances. The public would see only the mundane explanations, the natural interpretations, while behind closed doors, very different conversations occur. This is not conspiracy theory. This is how national security functions when confronted with unknown, potentially significant phenomena. And if ATLAS is significant, if it represents a challenge to our understanding of our place in the cosmos, then the silence, the controlled messaging, the subtle urgency, all make sense. They're not hiding aliens. They're managing uncertainty in a situation where premature disclosure could cause more harm than good. And we, watching from outside, can only infer from the patterns something about 3I-ATLAS changed the game. Part 13, 20. 25 AI breakthrough. Autonomous astrophysics models detect anomalous trajectories. Artificial intelligence has quietly revolutionized astronomy over the past decade. Machine learning algorithms trained on millions of labeled images now classify galaxies, identify exoplanet transits, and detect supernovae faster than human researchers ever could. Neural networks sift through petabytes of survey data, finding patterns invisible to human intuition, uncovering correlations that traditional statistics miss. In 2025, several research groups deployed autonomous astrophysics models, AI systems designed to analyze archival sky survey data without human supervision, flagging anomalies for further study. These systems, trained on decades of observations spanning billions of objects, learned what normal looks like. And in learning normal, they became exquisitely sensitive to abnormal. Trajectory outliers appeared in the anomaly lists almost immediately. The AI identified hundreds of objects across decades of data whose orbits didn't fit standard categories. Most were data errors, misidentified stars or cosmic rays that created false trajectories. But a subset, a small but persistent fraction, represented real objects with unusual motion. Some were long-period comets with perihelia far from the Sun, barely interacting with the solar system before receding. Others were objects with hyperbolic trajectories, passing through once without returning, potential interstellar visitors that predated Oumuamua but went unnoticed at the time. The AI flagged them not because humans programmed it to look for interstellar objects, but because their trajectories statistically deviated from the distribution of known solar system bodies. Machine learning's strength is pattern recognition. Humans excel at reasoning and hypothesis formation, but struggle with high-dimensional pattern spaces. AI excels at finding correlations in data too complex for human visualization. When trained on orbital elements, photometric light curves, and spectroscopic features, simultaneously AI can identify clusters of similar objects, even if those clusters don't correspond to known categories. In the 2025 analysis, one cluster stood out: objects with hyperbolic orbits, low perihelion distances, and anomalous brightness behaviors. The cluster included 3I-ATLAS. It also included several previously uncatalogued objects from archival data, suggesting ATLAS isn't unique but part of a population we've been missing. The AI classified 3I-ATLAS as non-standard, not comet, not asteroid, but something the training data lacked sufficient examples to categorize. This is both profound and frustrating. The system recognized ATLAS as different without being able to articulate why in human terms. Its internal representation, a multidimensional vector in neural network activation space, placed ATLAS far from known comets, but didn't map cleanly onto any labeled category. Researchers examining the classification found that ATLAS occupied a region of feature space characterized by high symmetry scores, tight coma confinement, and brightness variability not correlated with heliocentric distance. These are exactly the features human observers noted, but the AI discovered them independently, without bias or preconception. Classification systems for solar system objects have evolved over centuries. Asteroids are rocky, orbit in the inner solar system, and show little to no outgassing. Comets are icy, develop comae and tails near the Sun, and often have eccentric or hyperbolic orbits. Trojans share orbits with planets. Centaurs orbit between Jupiter and Neptune, showing transitional behavior. Each category has fuzzy boundaries, objects that don't quite fit, but the framework organizes thousands of known bodies effectively. AI classification doesn't rely on these human-defined categories. It discovers categories from data, clustering objects based on observed features. When 3I-ATLAS falls outside all clusters, it suggests the object genuinely doesn't fit our taxonomy. It's something else. The risk of AI misclassification is real. If the training data lacks diversity, the AI might label rare but natural phenomena as anomalous, simply because it hasn't seen enough examples. Interstellar comets are rare. Before Oumuamua, we had 0 confirmed examples. Training data drawn from solar system objects wouldn't include interstellar characteristics, so any interstellar visitor would appear anomalous. But the AI also flagged ATLAS for features unrelated to its trajectory. The symmetry, the brightness spikes, the coma morphology. These aren't intrinsic to being interstellar, they're intrinsic to ATLAS itself. The AI recognized that ATLAS behaves differently not just from solar system comets, but from all comets in its training set, including models of what interstellar comets should look like. The value of AI in astronomy extends beyond classification. AI can generate hypotheses, proposing physical mechanisms that might explain observed data. Generative models, trained on physics simulations and observational datasets, can suggest which combinations of parameters, composition, rotation, magnetic field strength might reproduce ATLAS's features. Early results from such models indicated that reproducing the observed symmetry and toroidal morphology required either extreme rotation rates combined with high tensile strength, or moderate rotation combined with magnetic confinement. Both scenarios are edge cases, possible but improbable. The AI, in essence, confirmed human intuition. ATLAS is weird, and explaining it requires invoking conditions rarely encountered. Clusters of anomalies across decades suggest ATLAS is part of a pattern. If the AI identified similar objects in archival data, objects that pass through the solar system unnoticed or misclassified, it implies a population of interstellar visitors more common than we realized. Some might be natural, ejected from other star systems by planetary interactions. Others might be rare configurations, icy bodies with unusual rotation or composition that produce a typical comet. And a very few might be engineered probes or derelicts drifting through the galaxy, occasionally passing through star systems, briefly visible before fading back into the dark. The statistical analysis remains preliminary, but the hint of a population raises stakes. If ATLAS is one of many, studying it becomes even more urgent. Public awareness of AI discoveries in astronomy is minimal. Papers describing AI-flagged anomalies appear in specialized journals, read by hundreds of researchers, not millions of citizens. The results percolate through academic communities slowly, debated, refined, sometimes dismissed. But the infrastructure for rapid discovery is now in place. As sky surveys like the Vera Rubin Observatory come online, generating terabytes of data nightly, AI will become the primary tool for first-pass analysis. Humans will follow up on AI-flagged targets, but the initial detection, the recognition that something is weird, will happen algorithmically. This changes the pace of discovery. Anomalies will be detected faster, studied sooner, and the window for institutional control of information will narrow. If another ATLAS-like object appears tomorrow, amateur astronomers and AI systems will flag it simultaneously, and the conversation will be public from the start. The convergence of science, AI, and 3I-ATLAS points toward an uncomfortable conclusion. The tools we've built to explore the universe are revealing that the universe is stranger than our frameworks accommodate. ATLAS challenges our taxonomy, our physics, our assumptions about what's possible. And AI, blind to our biases and expectations, confirms that the challenge is real. The object doesn't fit. It occupies a unique region of feature space, alone or part of a small, previously unrecognized population. And whether that population is natural or artificial, its existence demands we expand our understanding of what's out there, drifting between the stars, occasionally passing close enough for us to see. Part 14, the new fusion probe concept, revealed. This month. Fusion propulsion has been a dream of aerospace engineers since the mid-20th century. The energy density of nuclear fusion, the process that powers stars, dwarfs chemical rockets by orders of magnitude. A spacecraft powered by fusion could theoretically accelerate to a significant fraction of light speed, making interstellar travel feasible within human lifetimes, or at least within centuries. The challenge has always been confinement. Fusion requires temperatures exceeding tens of millions of degrees, hot enough that any material container would vaporize instantly. Magnetic confinement, trapping plasma in invisible magnetic bottles, offers a solution. Tokamaks and stellarators, experimental fusion reactors on Earth, use toroidal magnetic fields to confine plasma long enough for fusion reactions to occur. In November 2025, a research consortium announced a new fusion probe concept, a spacecraft design that uses toroidal plasma loops not just for power generation but for propulsion. The design is elegant and eerie. Instead of generating thrust by ejecting mass through a nozzle, the fusion probe uses magnetic nozzles to shape plasma exhaust into a directed jet. The magnetic fields confine the plasma in a toroidal loop around the spacecraft's midsection, heating it with radio frequency waves until fusion ignition occurs. The resulting energy heats the plasma further, and magnetic field gradients direct the flow rearward, generating thrust. From a distance, the spacecraft would appear as a glowing toroidal ring surrounding a central core, the plasma emitting light from fusion reactions and recombination events. The resemblance to 3I-ATLAS blue halo is unsettling. Same shape, same glow, Same tight confinement around a central nucleus. Toroidal fields help stabilize high-energy plasmas by eliminating endpoints where plasma could escape. In a linear magnetic bottle, plasma leaks out the ends. In a toroidal configuration, there are no ends. The field lines loop back on themselves, creating a closed system. This topology minimizes energy loss, allowing the plasma to remain confined for extended periods. It's why tokamaks use toroidal shapes. It's why the fusion probe concept adopts them. And it's why, if an interstellar spacecraft were designed to use plasma for propulsion or shielding, a toroidal configuration would be the natural choice. Nature sometimes mirrors engineering because both are constrained by the same physics. The shapes that minimize energy, that maximize stability, recur across scales and contexts. The concept allows interstellar travel by combining propulsion and power generation into a single system. The fusion reactions provide electricity for onboard, systems and thrust for acceleration. By varying the magnetic field strength and plasma density, the spacecraft can throttle thrust, adjusting velocity and direction over decades or centuries of travel. The system is robust, requiring no moving parts in the harsh environment of space, only magnetic coils and plasma injectors. Such a design could theoretically operate for thousands of years, limited only by component degradation and fuel supply. If an advanced civilization developed fusion propulsion, this or something similar might be their solution. And if they launched probes into the galaxy, those probes would glow with toroidal halos, visible across light years to anyone watching. The comparison with ATLAS is speculative but grounded in observation. ATLAS has a toroidal halo. The fusion probe concept predicts toroidal halos. ATLAS brightens independently of solar heating. Fusion reactions generate light independently of external energy sources. ATLAS shows tight plasma confinement. Fusion systems require tight plasma confinement. The parallels don't prove ATLAS is a fusion-powered craft, but they demonstrate that if it were, it would look much as it does. This is the uncomfortable space where engineering and observation overlap, where speculation becomes plausible because the data fits multiple explanations equally well. NASA's interest in plasma propulsion concepts includes ion drives, Hall thrusters, and VASIM, variable specific impulse magnetoplasma rockets. VASIMR uses radio frequency heating to ionize propellant and magnetic nozzles to direct the exhaust, achieving high efficiency and variable thrust. It's been tested in laboratories and proposed for Mars missions. Scaling VASIMR to fusion temperatures and interstellar velocities is a massive leap, but the principles are the same. Generate plasma, confine it magnetically, direct it for thrust. The fact that these technologies exist, that humans are developing them, means the physics is sound. And if we can conceive them with our current understanding, civilizations with centuries or millennia more experience likely perfected them. Magnetic nozzles and plasma mirrors, concepts explored in fusion propulsion research, shape plasma exhaust into directed beams. Plasma mirrors use magnetic fields to reflect plasma, bouncing it back and forth to increase confinement time or direct flow. These techniques appear in designs for advanced propulsion systems, space-based power generation, and even planetary defense concepts like deflecting asteroids with focused plasma beams. The engineering is real, tested in laboratories, demonstrated in principle if not yet at scale. If 3I-ATLAS uses similar techniques, it's doing nothing humans haven't conceived, just doing it better, at larger scales, or with greater efficiency. The concept allows interstellar travel by solving the two critical problems: energy and time. Fusion provides energy density sufficient to accelerate a spacecraft to relativistic speeds. Magnetic confinement allows that energy to be controlled and directed over timescales measured in centuries. Together, they make interstellar travel engineering rather than fantasy. If ATLAS is such a craft, its presence in our solar system means someone, somewhere, solved these problems. They built it. They launched it. And now, thousands or millions of years later, it passes through our neighborhood, a ghost of a civilization that might be thriving or extinct, unknowable across the light years. The convergence is what chills. This month, engineers unveil a fusion probe concept that looks like 3I-ATLAS. This year, ATLAS exhibits behaviors consistent with that concept. The resemblance isn't vague. It's specific, detailed, structural. Physics favors certain shapes. Toroidal confinement is one. If nature and engineering both converge on the same solution, then distinguishing between them becomes impossible without closer inspection. ATLAS might be a natural comet encountering rare conditions that mimic fusion propulsion signatures. Or it might be the real thing, a probe, ancient and forgotten, still executing its mission. The data doesn't let us choose, and that ambiguity, that inability to definitively say what we're looking at, is perhaps the most unsettling aspect of the entire mystery. We see something that looks engineered, behaves like a system, and matches our own speculative designs, and we can't prove it's anything more than the universe playing tricks on us, showing us our own dreams reflected in ice and plasma. Part 15, the 2025 Dust Arc Discovery in Outer Solar Space. Space is not empty. Even in the vast regions between planets, microdust particles drift, remnants of comet trails, asteroid collisions, and interstellar material swept up by the sun's gravity. These particles are tiny, micrometers to millimeters in diameter, but at the speeds objects travel in space, they're hazardous. The International Space Station's Whipple shields protect against impacts from particles travelling at orbital velocities around 8 kilometers per second. At interstellar velocities, 50 or 100 kilometers per second, the kinetic energy scales devastatingly. A grain of sand becomes a bullet, a pebble becomes a bomb. For any object travelling between stars, dust is an existential threat. In late 2025, analysis of data from the New Horizons spacecraft, now billions of kilometers beyond Pluto, revealed a previously undetected structure, a massive dust arc spanning a region of the outer solar system. The arc, diffuse and low reflectivity, had gone unnoticed in earlier surveys because its particles are dark, absorbing rather than reflecting sunlight. Only by analysing the faint glow from sunlight scattered at extreme angles did researchers detect it. The arc's existence raised immediate questions. How did it form? How long has it been there? And critically, does it pose a risk to objects passing through it? Dust arcs form from dynamic processes, collisions between larger bodies generating debris, gravitational resonances concentrating particles into specific orbits, or tidal disruption of comets creating trails. The newly discovered arc's origin remains unclear. Its location, beyond the Kuiper belt but within the heliosphere, suggests it might be primordial, material left over from the solar system's formation that never accreted into planets. Alternatively, it could be recent, the result of a collision between Kuiper belt objects within the last few million years. Either way, its presence means the outer solar system is dustier than models predicted, and objects travelling through it face higher impact rates than expected. For interstellar objects like 3I-ATLAS, entering a dustier environment changes the survival calculus. If ATLAS has been travelling for millions of years through the sparse interstellar medium, its shielding, whether natural ice layers or engineered protection, would be optimised for low particle densities. Encountering the dust arc means a sudden increase in impact rate, potentially thousands of times higher than in interstellar space. Without additional protection, the object would erode rapidly, its surface ablating under the relentless barrage. The fact that ATLAS appears intact, its coma tightly confined and symmetric, suggests it's managing the dust environment effectively. Plasma bubbles as shielding appear in both natural and engineered contexts. Comets naturally generate plasma tails, ionized gas pushed away by solar wind, which can deflect incoming charged particles. But neutral dust grains aren't affected by magnetic fields unless they're also charged, which requires ionization. If ATLAS is generating a plasma bubble dense enough to ionize incoming dust particles, charging them before impact, then magnetic fields could deflect them. This requires energy, continuous power to maintain the ionization and magnetic field strength. A passive comet couldn't do this. An active system could. Spacecraft shielding limitations are well documented. Current designs protect against particles up to about 1 centimeter at orbital speeds. But scaling that protection to interstellar speeds requires exponentially thicker shields, adding mass that makes missions impractical. Advanced concepts propose using electric or magnetic fields to charge and deflect particles, lightweight solutions that work if you have sufficient power. The fusion probe concept discussed earlier incorporates magnetic shielding as part of the propulsion system, using the same magnetic fields for both thrust and protection. If ATLAS is such a craft, its toroidal halo isn't just propulsion exhaust, it's armour. Dust arcs affecting long-period comets would be observable as increased coma activity when comets pass through dustier regions. Impacts heat surfaces, triggering outbursts, expanding comae, brightening the objects. Historical comets show variability, but it's usually attributed to internal processes, subsurface ice vaporizing as heat penetrates. If external dust impacts contribute significantly, we'd expect correlation between coma brightness and known dust structures. Searching archival data for such correlations is ongoing, but preliminary results suggest some comets do brighten when passing through predicted dust concentrations. ATLAS, however, doesn't show chaotic brightening. Its brightness spikes are controlled, periodic, suggesting active management rather than passive response to impacts. The discovery ties together the entire narrative. Solar magnetic dimpling creates unusual plasma environments. Radar upgrades aim to characterize objects in those environments. AI detects anomalous trajectories suggesting a population of unusual objects. Fusion probe concepts predict toroidal plasma shields. And now, a dust arc discovery explains why such shields might be necessary. Each piece, independently plausible, forms a pattern. ATLAS enters a solar system more complex than we realized, navigates magnetic anomalies we're just now detecting, exhibits shielding consistent with concepts we're just now engineering, and behaves in ways our best AI systems flag as non-standard. None of this proves artificiality. All of it suggests something extraordinary is happening. If 3I-ATLAS is just a comet, it's the strangest comet ever recorded, exhibiting every trait that would make us suspect artificiality without quite crossing into undeniable proof. It maintains symmetry that demands active regulation. It confines its coma in ways natural physics struggles to explain. It spikes in brightness independently of solar heating. It survives environments that should shred it. And it does all this while looking, from certain angles, exactly like a fusion-powered spacecraft with magnetic shielding. The alternative, that ATLAS is an engineered object, a probe or derelict travelling through the galaxy, fits the data at least as well as natural explanations. But accepting that alternative requires accepting that we're not alone, that intelligence exists or existed elsewhere, and that its artifacts occasionally pass through our cosmic neighbourhood. That's a threshold most scientists hesitate to cross without overwhelming evidence. The story of 3I-ATLAS is still unfolding. Observations continue, data accumulates, AI systems refine classifications, engineers develop concepts that mirror what we observe, and the mystery deepens, not because we lack information, but because the information points in directions we're unprepared to follow. Sometimes anomalies are noise, glitches, misunderstandings that resolve with better data. Sometimes they're signals, real phenomena demanding new physics or new frameworks, and sometimes, rarely, they're messages, intentional or not, from intelligences we've never met, artifacts of civilizations we can barely imagine drifting through the void, waiting for someone curious enough to notice. 3I-ATLAS might be rock and ice shaped by chance into something that looks designed. Or it might be exactly what it looks like. A traveller, ancient and purposeful, executing a mission we can only guess at, crossing our path for a brief moment before vanishing back into the dark. The data doesn't let us decide, and maybe that's the point. Maybe the universe offers mysteries not to be solved, but to remind us how much we don't know, how vast the cosmos is, and how much remains to discover.